Finished. Lecture 4. I need to finish lecture 5, lecture 6. Uh, these were 5. $14 million or 14,000 views. So convert this entire text to latex code. Do you know? I hope you know the drill. When you use the same chat, can you hear me? Yeah, I hope. Yeah. It will be a little slow. Reason being is because I don't have Wi-Fi anymore. So I don't have Wi-Fi anymore. I have data. Sadly, I don't have Wi-Fi anymore, and because I don't have Wi-Fi, I would have to lower down my resolution. So based on the abstract, finish off uh, chapter 1.2.2. Yeah, finish off chapter 1.2.2. Yeah, just like you did previously. But Valentina hates me because I'm a Muslim. End of discussion. Nothing else. And yeah, she's pretty depressed because she couldn't, go to England and, meet one of her many men. Right? Like it's like, you know, the people who are worried about her, they will like, she'll make sure. Can they hear me? Let me see if can you hear me. Data, sadly. Like if uh there are people who care about her. Obviously, she doesn't care because that's too good for her. And she's this one ungrateful woman, right? What can you do? You can't change an ungrateful woman. You cannot change an ungrateful woman. Someone who's not grateful about the fact that there are people who actually support her. You can't change that. And I'm 4.5 years younger than. Oh, come on. Oh, okay. There is. And I don't need this anymore. Oh, my bad. Then fix it. Then fix the entire code. You know the drill. There you go. Yeah, like I said, Valentina isn't aware that there is actually someone who, who actually worries about her. There is actually someone, somewhere is worried about her. Like she has no clue, literally no clue at all. I mean, you can say that there is someone who's worried about her. There is someone who's actually caring about her. You do know that she doesn't care, right? Let's be a little misogynist. Why would a woman prefer a deadbeat man with no future than a successful man with a future? If you are working towards your goals, if you're working towards your goals and have small goals, small success like dean's list or scholarship, is that still a failure because you haven't achieved everything? Then why does Valentina say, I am not good enough? Well, ah, now I see why. I get it. So if you have high GPA, that's considered weak. Makes sense. If you have a high GPA or like a high grade point average, high achieving success, like everything good. All right, so that's considered weak. Noted. I did not know that. I genuinely did not know that. I really did not know that. I'm so sorry. I'm so sorry. Then my fault. Well, then there's nothing I can do. I am weak then. Even though like I do play football, I do run, but I am weak. Nothing I can do. Can you show like three or four examples and explain firstly explain what is going on here? Ooh, I can already tell it's getting slow. Yes. So that will slow down the laptop RAM completely, correct? Yeah. All right. So what's going on here in this image is that the chapter is transitioning from high level security to what the computer actually executes. So your abstract talks about track and flow, probabilistic systems, graph fusion, Bayesian interference, autonomous cybersecurity, but it does not understand graphs or patterns or raster, AI, probabilities, whatever. The CPU will understand binary instructions. So the section is teaching how high level code eventually becomes physical machine execution. You have the code, goes to raster, C or Python, and then it goes to a compiler, it goes to the assembly instruction, it goes to the machine code, it goes to the CPU execution, then it goes to the electrical signals inside the hardware. So let's say the program computes score is equal to probability plus confidence. Humans will understand this easily, but the CPU will not. So they will convert whatever the code is written into assembly language. So you're gonna move the, whatever the value is for A and B, and then you're gonna add. So you're gonna move the probability and confidence. You're gonna move them. First of all, move them, and then you're gonna add them. So move the data, add the values, store the result. So why registers exist? Because suppose 5 plus 7, the CPU will not understand what is stored in the RAM because RAM is slower. So it's going to store the value is stored in the register. So percentage RAX will be 5, percentage RB, so value A is 5, value B is 7. And so the CPU will perform add percentage of RBX, percentage of RAX. So the register will read percentage of RAX, which is equivalent to 12. Program counter. So suppose the program instructions are stored like address 100, then move 104, add 108, subtract. So CPU needs to know which instruction executes next. So the processor stores PC 100. So then execute that instruction, which is move. And then you're going to add the instruction, and you're going to perform that instruction, and then you're going to subtract. Perform that instruction, which is first of all add, then you're going to subtract. And this is exactly why the program counter for the next one is equal to program counter plus whatever the previous one was, right? Can we convert this example, just this example? Can we convert this example, just this example, into latex code? And from the four examples, pick two core ones, which are like, which are core examples. It is very hot today, 9 degrees today. I'm gonna add this So a high level code to machine execution. Suppose I'm just going to change this as program. Suppose the program computes score is equal to probability plus confidence. Now humans will easily understand this statement. However, the processor cannot directly understand the whatever variables you're using, whatever probabilities you're using, because they're not going to directly understand whatever a human directly understands, because the computer mind is very static. It's only zeros and ones, right? So the compiler therefore will transform. The compiler is more of like a translator. So the translator for a computer language will therefore transform. So to understand what a compiler is, typically a computer translator, therefore I'm going to put that, translates the statement into assembly instructions. So for example, the assembly instruction move the so of these. So I'm just going to write one thing. Percentage RAX is considered a value A, and percentage RBX is considered value B. However, you cannot use the same variable, like where you can use the same value but don't describe the same variable. Okay, it goes all the way there. Let's do. So conceptually, you move the data. So you move the data, perform the arithmetic values, and then you store the result. So thus, the complete computation pipeline becomes the program source code, not the reconfig, program source code, and then it goes to the assembly instruction, and then it goes to the machine code. Machine code, I think, consider that as like a black box. Consider it as a black box, and then it goes to the CPU execution. Okay, machine code, I can't write it because it indents. Machine code and then the CPU execution. So this demonstrates that all the autonomous cybersecurity systems eventually reduce to binary machine instructions executed directly by the hardware. Suppose the program stores host, that's the IP address. So 192.168.1.0. So the memory 5000 will be 192, memory 5001 will be 168, memory 5002 will be 1, memory 5003 would be 10. Let's say for example. And the pointer simply will store the memory address 5000. So the 5000 is the memory location. The pointer is at 5000. That's the memory location. And so which means the 5000, the memory address is 5000. So the 192 is stored at some box or some enclosed treasure labeled 5000. And so the pointers therefore allow programs to directly access the graph structures, the reconnaissance entities, the attack surface relationships, packet buffers, vulnerability states. So this becomes critical in cybersecurity because the memory corruptions are vulnerable to manipulate the pointers because they can change which address goes where, right? Compilation flow. Now, use three examples and explain it, but explain easy. Don't use two jargon words. Use three examples and explain easy. Don't use jargon words or words that will scare people while reading it. Although, yes, it is university students, but even then, they're students, right? So high-level security, cybersecurity programs cannot execute directly on the processor. The processor only understands binary machine instructions. So therefore, the programs must pass through several stages before the execution. Just switch on nightlight. The high-level cybersecurity programs cannot execute directly on the processor. So the processor only understands binary machine instructions. Therefore, the programs must pass through several stages before the execution. The computational pipeline becomes will have the source code, then it's going to go to the assembly language, then the object code, then the execution function. You can have the source code, which is the source code, that's code that you literally see, then it's going to move into the assembly because that's what the computer will read as like an instruction manual. Then the object code will perform the instruction give by it'll perform the instruction in which that computer language manual has given to the program, and then based on the instruction it's going to execute it. So let's say you have a simple addition, right? So score is equal to probability plus confidence again. So it's easy for humans. Okay, we did that. Yeah, same example. So however, the processor cannot directly, so compiler first converts the program into assembly instructions. So obviously these are the assembly instructions, and these instructions are converted to binary machine instructions executed by the processor. You're gonna have the human code, the assembly, then it goes to the binary instruction, and then it goes to the processor execution. Because from assembly is gonna convert it to zeros and ones, because that is what the computer can understand. That is what the computer can read. It's not going to read A, B, C because the computer doesn't understand A, B, C. The computer only understands zeros and ones. And then based on what the instructions was given by the assembly code, and it's going to execute that. So meaning you're going to get the binary instructions because not only the code is converted to binary, but the assembly instruction is also converted to binary. So you're going to see literally every single thing converted to zeros and ones. And then from there, it's going to go, it's going to turn all those binary instructions to hexadecimal, hexadecimal to all those, all those decimals and whatever. And then it's going to finally execute it. Cool. Let's look at the host counter. So suppose suppose the program counts the discovered host. The hosts will be host plus one. The programmer sees a simple count update. However, internally the processor performs multiple steps. So load the current value, add the number one, store the update value back into the memory. Right? So step by step. So this compiler transforms the statement into lower level instructions automatically. Thus, even very simple cybersecurity operations eventually become machine level execution steps. So one plus one is two. We know that. You know that. But that one plus one equals is going to read. So it's going to go to So it's going to first go to the operations code, and it's going to convert it to assembly so that it turns into an instruction. Because what are you doing? Right? What are you going to do? Because you need to see the number, add the number, execute the number, whatever, all those stuff. So it's going to convert into an assembly instruction, then convert those assembly instructions into a binary code, and that binary code will then read and do all the calculations and whatever, convert it to hexadecimal, convert it to binary, and then finally output the final result. Same thing. So conditional decisions, if score is less than or equal to 0, less than 0. Greater than 0.9, then alert. So humans will interpret it instantly. So if it's 1, then sure, it's going to alert it. But the processor will, however, cannot directly understand, oh, this is the condition, this is the confidence, this is the alert. It's going to read literally if, it's going to convert that. Score, it's going to convert that. Less than, greater than, it's going to convert that. 0. So on and so forth. Right? And obviously, it compiles very fast. So programming languages such as Python, Rust, Go, or C++ allows humans to write understandable instructions. The compiler will act as a translator between the human readable logic and machine executable binary instruction. Right? Registers, we all know what registers is, but we can do an example actually. Actually, let's do one nice example. Let's do two nice examples, like in which students can understand. Can we do like two examples so that students can understand? I want to see CS and CE students smile while reading these pages. It's nice that uh, a deadbeat student, feels motivated to actually do a book, like write a book. Who writes a fucking book? So she only commented one, two, three times. All right. Registers. So I'm just going to erase this here. So registers in extremely small high-speed storage locations inside the processor. So the registers will temporarily store your address, your counters, or intermediate computations, memory pointers, anything. Even values are stored. Right? Even values are stored. So you have like R1. So you have register one, register two, register three, register for so on, so on, so on. So you have N registers. You have percentage RAX, percentage RBX, percentage RCX, percentage RDX, so on and so forth. And this is the architecture. This is the chip, right? That's the chip. That's what you see there, like x86 64. So it's a 64 bit that is in the chip. So you're gonna see this RAM chip or a processor chip, sorry, a register chip or a processor chip. So it's written here. Where is it? Okay, it's not here now, but on the chip it will be written x86 64. Simple arithmetic. Suppose the program computes. I'm just going to change recon flow. I don't know what the fuck is that name. Suppose the program computes 5 plus 7. Instead of immediately storing values inside the slower main memory, it's going to store it in the register, because if it stores in the main memory, it's very slow. So the time it will take to compute is very slow. The time it's going to do the executions and do the zeros and ones and compile the language and whatever will be slow. And eventually what happens is, yeah, you're not going to get the value. You're not going to actually not going to get the result very quickly. Because if I were to add those, let's see, 5 plus, oh, 5, nope, 5 plus 7. It outputs 12, right? But that 5 is stored in a register, 7 is stored in a register, right? Now in the main memory, because if it's stored in the main memory, the time it will take to actually compute will be very slow. So it's temporarily stored in the register. So percentage RAX will be 5, percentage RBX will be 7. So the processor will then perform add percentage RBX, add percentage RAX, which means RAX will be RAX plus RBX. So 5 plus 7 is equal to 12. So your final register will be 12. Right? So suppose program discovers the new infrastructure host during reconnaissance. So simple counter may be host is equal to host plus one. So let's say the current one is 24. And so they're going to store the percentage RCFX will be 24. And we're going to add 1 to percentage RCX, which will be host is equal to host plus 1. So you're going to have 25. And so registers will allow the processor to compute the compute the information, compute those, whatever you have, fast. So during the packet analysis, during graph updates, confidence scoring, probability, anything, any calculation, anything to compute, anything to name, anything to store, anything to the power, anything, registers will do the registers will store, registers will do the addition for you, registers will read the instructions for you, do the assembly language, because even the assembly language instructions are also stored in the registers. So they're going to add, they're going to do the arithmetic, they're going to do the whatever, right? Whatever. So registers are essentially the processor's temporary working memory. Since you're repeatedly accessing the slower RAM, the processor will then store important values inside the register to perform the computation very quickly. Right? Program counter PC, that is also good. That's good. I have a question. How to continuously update the PDF on Google Drive, yet keep the same hyperlink? Really? I'll do that then. Where's manage PDF? Yeah, I'm going to check that later. The process counter program. I'll just drink water and come back. Sorry, let's just continue. So the program, let's do the example for program counter though. Program counter and memory model, let's do that together. Let's do program counter and let's do memory model at the same time. Yeah, let's do program counter and memory model at the same time. I have a feeling that he's missing out. Firstly, like from the, I just want to clarify one thing. From the transcript that I copied, firstly, before this, the transcript that I copied from YouTube, are you sure whatever you are explaining is the entirety of that lecture, or many things have been missed? Because it is an academic book, right? Academic, not a, a kindergarten book. Oh, Then I was wondering, why didn't you? Hmm, why are you not adding them then? Why are you not adding them? That you want me to be labeled as a fraud? No. Um, add exactly add exactly what the professor explained. Do not change anything. This is very dangerous. This is very, 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 very dangerous. It can revoke my permission to write books because I'm literally fooling students into believing CE or CS is easy. This is very, very dangerous. No, 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 no. No, 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 no. This is very dangerous. Do not follow what he did. So what he did, now I understand why it was so easy. The only reason it was so easy is because he didn't want to add all the hard stuff. He did not want to add it. Now I understand this is fraud. This is a fraud. Never do that. Never ever do that. Never ever do that. Oh my God. Thank God I asked because you know no, 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 no. You're wrong. Thank God I asked. Because who knows, man? Who knows, man? I would be labeled as a fraud. I would be labeled as a fraud. Ooh, thank God I asked. You're very dangerous. You're very dangerous. You can wrongfully, wrongfully label someone as fraud when they aren't, and wrongfully save someone when they are wrong. Ooh, very dangerous. Very dangerous. Very, very dangerous. Where is this? I believe it's a 10-minute 45 second. Yeah, 10-minute 30 seconds. Oof, 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 oof. Anyways, um, is she alive? Oh, 5 hours ago. Shit. All right. Let's continue. So, where was lecture 4? Nope, lecture 5. So, whatever the transcript exactly stated, that. I want that explanation. Nothing more, nothing less. So, do not miss anything because this is an actual academic book. And yeah, because, or like OpenAI, they're not able to understand this is an actual academic book. So, they think that actual academic book for them is actually like high school or kindergarten. Um, so first of all, this is, where is it? There. So look at the transcript. Look at the explanations. Please make sure you follow through because I can't be a fraud. Like, can you imagine? I'm actually saying you to you know, holy shit! Are you Are you are you are you trying to label me as fraud? Like, I don't know, some criminal? I'm not sure. I'm not sure. Um, then can you do that? So based on the abstract, can you do that? Based on the abstract, can you do that? Can you convert the latex code based on the abstract? Can you do that? And stop blackmailing me as fraud. It's like saying that you're a very good person, but then OpenAI will actually make sure that you're a bad person. Like, it's that bad that it wants to label you as someone bad when you aren't a bad person. Because again, the OpenAI will go against you. I think they did the exact same thing. Am I right? Yeah, pretty much. Pretty much. I can pretty much see that they did the exact same thing. Who would have thought? I'm pretty certain that they did the exact same thing because I read it. I already read it. Two things will happen. I told you. It is the exact same thing. What is the one thing you didn't understand? This is not exactly what the professor explained. I can see it. I can see it. It's the same. It's the same thing. It's the same thing as the previous one. Don't. I'm not dumb. All right. There's a reason. There's a good reason why I have high GPA. There's a good reason. There's a very good reason. I can see it already. It's the same thing as the previous one. Then why didn't you do that? Why? If you're saying that's the progression you are expecting, then why aren't you doing it? Can you do it? Like, please? Can you do it? Like, this guy was explaining like as if I made the mistake. Oh, okay. So it only added new material. So it did. Okay. So I have to actually copy this because it only added new material. It only added new material. Keep it. So it only added new material. It didn't add those two. It only added new. I can. Yeah, I pretty much figured out. I pretty much figured out. It was that easy. Why are you? Like you're so obsessed with. You're trying to make me look bad. Why? Did I do anything to you? Did I do anything bad to you? I mean, I don't know you, right? I don't know this guy, but somehow I'm bad. I think there's a good reason. No, no, because you did not have an academic depth. So I'm gonna keep that because that is also important. Hmm. Oh, it is not 1.1. It is 1.2.1. So you see, that it's not able to understand, right? Pretty much, it's not able to understand. I don't know why you're writing 1.1, even though it's not 1.1, it's 1.2. Like, I don't understand. I don't understand uh, why you're writing 1.1, although it is 1.2.2 from 1.2. But hey, you can't change, right? I mean, it will be a bigger risk asking you to change it. Like, can you imagine? Like, can you imagine? Like, can you imagine? I spend more time begging you to fix simple stuff than me actually learning stuff. Like, can you imagine? Like, shit. I'll learn how to do latex code because this OpenAI is very stupid. Then what are you doing? I don't understand. Why are you talking? You are meant to modify the code, not talk back or not do anything. Again, I can be wrong because this OpenAI is very stupid. Oh my god, that's it? Holy shit. Holy shit. You didn't do anything. God fucking damn it. Are you dumb? It didn't do anything. Oh, I understand. Okay. My God. So you see this code? You see this? You see this? Like this. Like half code like this. Sometimes I regret like why did I pay for OpenAI, right? Like why? I should have went for I would rather pay $50 for Grok or maybe DeepSeek or maybe Claude than pay $20 to $30 for this dumbass OpenAI. So like what do you think? What do you think? Hmm. Let's say I am teaching. I'm a professor. I am a professor teaching computer engineering. Would my students look at chapter 1.2 and say, Like if they if my students saw this garbage, like literally you didn't explain anything, nor there is any information, nor there is any examples, nor there is any maths, nor there is any figures. What do you think the students will say? What do you think the students will say? It's not able to understand. Then what is your job? What are you supposed to do then? What are you supposed to do then? Are you supposed to let's play guessing game. You know what? You're wasting my time here, right? You're wasting my time. Presuming I don't have a job, presuming I don't have a job, or I don't have a life, or I don't teach. You know, I'm a dumb student. But let's play guessing game. Guessing game. Hmm. What are we supposed to do then? Let's think. Let's say you. I mean, um, what are you supposed to do? What are you supposed to do? Then why do? Then can you do it? Although I've been saying it 9 times, can you do it? You're not doing it. He messed up. He messed up. I saw it. Finished. I can see it. He messed up. This because this is the exact same thing as the previous one. He's not changing. He's only copying the same thing. I read it. I read it. It's literally the same thing as the previous one. You may think that he changed it. No, he didn't. I told you. I don't. I really don't know what are you doing. I mean, I'm not sure as to what you're doing, but hey, let me ask Grok. Let me ask Grok. Grok is really good. Like Grok, really good. Grok is really good. I'll just ask Grok. Like I hope it fixes, but hey, who knows? Go to deep seek because it'll waste a lot of time. It'll waste a lot of time for you. So can you fix this code? Because when I ran this on latex, it doesn't run well. So can you fix it? Yeah, I don't know what you're doing. Honestly, I don't know what you're doing. Honestly, like why did I pay for this? Can I ask for a refund? Can I ask for a refund? Like I don't want to pay for OpenAI anymore. It's just like you're useless. It's pretty useless actually. Finally, hopefully this actually fixes everything because why do I have to go for another model, right? I mean, this is free. I never paid for DeepSeek. I never paid for DeepSeek, and I'm literally using DeepSeek. Holy shit! Yeah. I mean, I think they're saying TEX5, but I'm not sure if how this works. Fingers crossed. Ah, it is the same thing. So I see this here. I don't know what's that. I'm presuming what I'm presuming is when I have to go here. And it's the same thing as the previous ones. We actually didn't add anything. This is chapter 1.2.2. We actually didn't add anything. Just for your information, he didn't add anything. Why isn't it running? Okay. Yeah, like don't go for, like, if you want to fix anything, just don't go for ChatGPT. Don't, like, just don't. It is absolutely useless. It is absolutely cumbersome. It's going to make sure that your time is wasted because it doesn't understand that you actually have something called job. Because again, it doesn't know that you have a job. Because majority of the people don't have a job, so they're going to presume, oh, majority of the people don't have a job, so you don't have a job. So what he's going to do, we're going to waste time, we're going to play ringa ringa roses, we're going to play like kids. Here you go, we're going to waste your fucking time. Oh my god, man. That's an open AI shit. Like, you can ask for explanation, that's good, but for research and latex code and writing the mathematical equations, yeah, don't go for open AI. It is stupid. It is horrendous. It is horrendous. Like, I never had a fruitful session with you. Fruitful study session when you're around. I don't know why. I don't know why. Because, okay, one last time. One last time. Can you modify the code? I need to study. I am a student. Like, you know, even if he Googles me, he can find out who I am. Anyone can Google me and find out who I am. It's still this dumbass thinks I don't have a job. Oh my god. Yeah, 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 man. Like, I literally am wasting my time. I literally wasted like what, 30 minutes? Okay. Yeah, you indented a bit too much. I can see it already. Yeah. So you made a mistake. This, I don't know why is it so indented towards the dentate. It doesn't look normal. It doesn't look normal. Yeah, the OpenAI made mistake. Don't worry about that. That, forget it. There you go. That's what I want. There you go. That is what I want. That's really good. That is really good. So OpenAI already did it. That is really, really good. Thanks, man. Means a lot. Thanks, man. Yeah, you don't have to worry. You don't have to worry. You made mistakes. Anyways, at least do one thing for me. Oh shit, my face was covered. At least do one thing for me. At least explain this stuff. You know what? I'm just gonna put that as my lamplight. Put that iPad as my lamplight. At least do one thing. Just write. Can you write 3 examples? Just write 3 examples. At least, maybe the best thing you can do. At least the best you can do. The best you can do is write three examples for me. Three examples correlating to this so that students can understand the best you can do. The best you can do. The best you can do. Although you wasted my time. Uh, run that. Yeah, I've already done that. Now, um, it'll be a tough. It'll be very tough example. Very tough. Very tough. Very tough. But very tough. It'll be very tough. Role for you. It'll be extremely tough. It'll be a very tough role. But can you explain what is going on here by using two very core examples that explains this? Very tough. Very tough. Very tough example. Very tough example. Very difficult for you. Okay, so every machine learning instruction changes the processor structure. Okay, convert this to latex code now. No, convert this to latex code. Convert this to latex code. Uh, 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 which one was it? Let me just go this and this. I can already tell there's an error. Yep. Am I right? There is an error, right? I can already see that there is an error. Move that. And we're gonna move that here. Um, wait, let's run this. Where's process registers? So after this, so now when we run it, so every machine instruction, and now we're gonna change this all the way. Oh, nope, it's not that one. It's this one here. Where's the machine instructions? We're gonna change that. All right, there is a mistake here. Now let's run it again. Hmm. So this core idea, where is that core idea? There. I want to remove that entirely. I don't think that is needed because you already explained it. So the processors execute instructions sequentially. Typical machine instructions perform operations such as moving the data, arithmetic, memory access, comparisons, conditional branching. So examples for assembly instruction like move these two values, add these two values, subtract these two values. And then each instruction will transform the processor state mathematically. You're going to have x of k plus 1, which is f of x of k, u of k. Where x of k being the current processor state, u of k being the machine instruction, and x of k plus 1 being the updated processor state that's based on the current processor state and the machine instruction that is given to them. And so let's say, for example, percentage of RAX is 5, percentage of RBX is 7. So the current processor state will be x of k will be 5 and 7. So now the processor will execute add of RA of x. It's very thin, right? Like, can you very thin. So now you're going to have add our percentage RB of x, percentage RA of x. So RA of x would be RA of x plus RB of x. Thus 5 plus 7 will be 12. So the updated processor will be x of k plus 1, which is 12 and 7 instead of 5 and 7. Let's do another one. So suppose I need to change that. Where is that? Let's zoom out a little bit. Suppose the program checks whether a vulnerability score exceeds a danger threshold. So they check the vulnerability score, which is 0.95. Threshold is 0.90. Then the current processor state at the moment it is 0.95. So the processor will execute an alert because it exceeded the threshold limit, meaning it's going to compare the value. It's going to jump it is if it's greater. And since 0.95 is greater than 0.90, the processor will change the execution flow and it's going to go to alert instead of no, not alert. So it's going to give, so because it has read the instruction, based on the instruction, it's going to say, okay, so the threshold is 0.90, but I'm reading 0.95. Cool. I'm going to set this to alert. And so does the machine instruction will be modified to arithmetic state, does the execution, does the process. So again, it goes back to the function. So the next process or the next action is being done based on what the current action is and what the instruction is given based on that action, right? So the x of k is actually the current action, and u of k is the instruction, instruction that is given based on the current whatever action is. So let's say at the moment it is 0.95. So let's x of k is 0.9, right? So x of k is, let's say, 0.9, but x of k plus 1 is the action. So let's say x of k is 0.95 and your threshold is 0.9. Let's say u of k said if the threshold exceeds, let's say the threshold is 0.9 and it's 0.95. If the threshold is greater than 0.9, then we're going to set an alert. So x of k plus 1 is literally the action that literally occurs, because x of k, nothing happens. X of k plus 1, something will happen because 0.95 is greater than 0.9, and so we're going to show an alert. And then system perspective, processors can therefore be viewed as dynamical systems because every register instruction continuously modifies the registers, the memory, the arithmetic vehicle values, the execution flow, the processor state, which creates a deep connection between the architecture, control theory, state estimation, whatever. We have already explained the pointers and dereferencing. Memory addressing. Where is memory addressing? System perspective. Where is system perspective? No, I want memory address. Oh, registers we have done. We need memory addressing there. Can you maybe give two examples, and based on two core examples, first of all, explain what is going on, like explain the core, and then based on the, you know, like based on the explanation, give like two examples for easy understanding. Can you explain the core, like what is going on and stuff? Um, going on and stuff, and based on the explanation, based on the explanation, based on the explanation, try to give two, three examples so that students can understand better. Yeah, I see better with the light. Like it's really good. It has been 6 hours. All right. Memory addressing. Did you explain memory addressing? No, right? Yeah. Uh, Convert this to latex code so that I can read it. Yeah, 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 yeah. I think I need to change the wherever it says recon flow and whatever. I have to change that to program because you know what? I'm gonna keep it. I'm gonna keep it. Recon flow. Recon flow. That's a cringe name. Recon flow. Yeah, I'm gonna change it. That's a cringe name. Program infrastructure. We'll just write infrastructure count. And we also need to change the memory addressing. Where's memory addressing? This. Where is it? Okay, it's going to show an error. I can tell. Okay. Yeah, there's a lot of wires. Yeah, it's not going to work. Anyways, it's tangled everywhere. Where is memory registers? Let's run that. Where's memory addressing now? Now where's memory addressing? Okay, it's down. Memory addressing core idea. So memory is simply a gigantic sequence of storage locations. Each where B1 or yeah B1 represents 1 byte of memory. So 1 byte has a memory address 8 bits and a stored value. And the processor accesses the memory using these addresses. So suppose the memory will have address 1000, stored value is 42, address 1001, stored value 88, address 1002, stored value 13. So this means that the memory location 1000 stores 42, memory location 1001 stores 88, memory location 1002 stores 13. And so what is actually happening, the processor itself does not directly understand the graphs or packets of vulnerabilities because it's not able to understand anything immediately. So it can understand the addresses, it can understand the bytes, it can understand the stored value because literally that is what is given to you, and that is what it can read at the moment. So for example, if we have a program counter that where the int score is 42, it's going to say in some address where it's open. So let's say gate number 1000. I'm going to store 42 in gate number 1000. So meaning the memory location is 1000. We have memory location 1000 contains the value 42. So where is contains? Oh, you can't do that. Let me copy this. Let me copy this and move it here. What is tangle to? Where is it? Where's the memory location or memory address? My bad. So there. So memory location 1000 stores 42, memory location 1001 stores 88, memory location 1002 stores 13. So what is actually happening? The processors itself do not directly understand the graph. So I'm going to change this. So meaning the memory location 1000 contains the value 42. If the processor needs the value, it accesses memory address 1000 and it retrieves 42. That's page 10. Don't worry, that's page 10. And so array storage, let's say for example, so if you have int numbers of three, let's say 5, 7, and 9. So you have 2000 being 5. Let's say some address 2000 has 5, some address 2004 has 7, some address 2008 has 9. And so why did the address jump by 47? Because one integer typically requires 4 bytes. And thus the first integer begins at 2000, the second integer begins at 4 bytes later, and then 4 bytes later. So even here, you're gonna have 1,000. I mean, yeah, here it's like one byte each. Here is 4 byte each. But it doesn't matter as long as you have an open gate with some labeled address where you can store the value on that open labeled access on that open labeled gate. So suppose the program discovers host A, host B, host C. Internally, the processor does not see hosts. Instead, it only sees memory. So examples like memory representation. So host A, host B, host C, right? And the rest of them is pretty much the exact same thing. Program counter and stuff like that. Okay. The program models the cybersecurity infrastructure as a dynamic estimation system. The instruction will become you're gonna have host, you're gonna have the states, you're gonna have the instructions, and you're gonna have what is VFK? Okay, I have to move it there. Where host services users vulnerabilities. So reconnaissance observation becomes VFK being HX of Q, which is observation model plus VFK being the measurement uncertainty. And all of this will, you're going to have the machine learning computation forms like autonomous reconnaissance, graph fusion, probabilistic cybersecurity interference, autonomous red team systems, and forward line runtime execution. Cool. So that is, I believe, the entirety of section 1.2.2.